So if you have access to these libraries, so you can have a look at the book. Uh, if you are interested in knowing the name of the book, so kindly be in contact with me so that I can tell you the uh, name of the book to the students who want to go through it. Anyhow, starting with the lecture which is scheduled for today. Just a moment. Okay, then I suppose my video is also clear. So if you are facing any problem regarding the audio or the video presentation, kindly inform me through the WhatsApp group, because when I'm delivering a lecture, I cannot have a look at the chat box. And the other thing is, I have taken the attendance also. There happen to be somewhere around 19 or 20 students, because I need to know who are the students who are not attending the class regularly. Anyhow, let's proceed with the lecture for today. Uh, in the following slides, we will discuss the various steps of FEM, and these steps of FEM are going to be discussed with an example. Since we are interested in a one domain solution, the domain itself is going to be represented by a line which has two ends, represented in this particular figure by 2 points located at XA and XB, while the domain itself has been indicated by a line. So let's just assume that the differential equation which is being solved in this particular domain happens to be a second order differential equation. In this particular case, u is the variable for which the solution is being sought, and obviously u is going to be a function of x also. Apart from this, the differential equation happens to be a second order differential equation, because u is going to be differentiated twice. So that makes the equation to be a second order differential equation. It is one dimension in nature, because there happens to be only x space coordinate, and it is a steady state equation, because there is no term of time in this particular differential equation. Apart from this, the domain starts from x is equal to 1 and ends at x is equal to 2. So for this particular differential equation, we are interested in finding the value of u, that is the unknown, for this domain. And the thing is that this particular differential equation represents plenty of phenomena. It represents a axial deformation of a bar. It can also represent a bending of a beam. It represents heat transfer also, and it can represent fluid mechanics problem also. So accordingly, the value of u is going to be different in different phenomena which we are interested in solving. For example, if you are interested in heat transfer problem, the variable u is going to be is going to represent temperature. Similarly, if we are interested in axial deformation of a bar, then u is going to represent the deformation. And similarly for the other fields. Now the other thing is that the solution of this equation is going to require certain boundary conditions also. And in this particular case, the boundary conditions are going to be prescribed at x is equal to 1 and x is equal to 2. and they can be, for this particular example, we have assumed that the value of u is known at point number at x is equal to 1, that is equal to 2, and similarly at the other endpoint given by x is equal to 2, the value of u is not known, but the value of du by dx, which represents flux, as we have done, as we have discussed in the previous classes, that is given. So u happens to be 1 by 2. And if anything is not clear, so kindly just post a message in the WhatsApp group so that I can explain the things to a larger extent. Anyhow, moving to the next slide. Now, in finite element method, we basically have a trial function. Just a moment. We have a trial function which most of the time happens to be a polynomial given by expression something like which is on display, in which you can notice that there happens to be phi naught, phi 1, phi 2. These are some polynomials of x. We are going to see in the future classes that what polynomials are going to be taken. And there are some unknown terms also, which are represented by a1 and a2, so on. So depending upon the accuracy which we desired in the finite element method, we can take a number of terms in the trial function. So this is the first step in the finite difference method, finite element method. In the next slides, we will substitute the boundary conditions in the trial function. We have two boundary conditions, one in terms of u at x is equal to 1, and the other in terms of du by dx at x is equal to 2. So in the coming slides, we will substitute the boundary conditions in this particular trial function to find the value of u over the domain. Also notice that in the trial function which is on display, there happens to be a first term represented by phi naught, which is not multiplied by any a. There happens to be a term phi naught. It is a polynomial, of course, but this particular phi naught is not multiplied by any term a. This is because phi naught is being used to satisfy the given boundary conditions. And how this is going to be done, that is obviously going to be illustrated to you in the future slides with the help of an example. So moving to the next slide. The first boundary condition is at x is equal to 1. The value of u is given, and this can be substituted in the trial function. That is, the trial function itself can be evaluated at x is equal to 1 to give you, to satisfy the first boundary condition. And the thing is, which has to be remembered is that in finite element method, we are going to get plenty of solutions. We are going to have more than one solution. And out of all those solutions, the particular solution which we are going to choose is the one which is going to reduce the error to the minimum possible. Okay? In finite element, we are going to have plenty of solutions. We are going to have plenty of solutions, And out of all those solutions, we are supposed to choose a one which has a minimum error. So if we are supposed to satisfy this particular equation on the display, then one of the possible solution is that phi naught at 1 is equal to 2, and rest of the functions given by phi1, phi2, phi3, etc., all of them evaluated at x is equal to 1 can be 0. So this obviously is one of the easiest solution which we can derive or which we can have without doing any calculations. That is the first boundary condition is satisfied by phi naught itself, and the rest of the term phi 1, phi 2, phi 3, etc., all of them are 0 at x is equal to 1. Now coming to the second boundary condition, which is in terms of the differential of u. This also can be substituted in the trial function after the trial function itself has been differentiated. Okay. And then again, the other possible solution is that this boundary condition is again satisfied by the by phi naught itself, and the rest of the terms such as d phi 1 by dx, d phi 2 by dx, etc., all these other terms themselves are 0. So the thing is that in terms of all the phi's which are appearing in the trial function, all the phi's and the differentials of the phi's are 0 at the 2 points where the boundary condition has been prescribed. The only thing which is not 0 at these two locations is phi naught itself, and therefore both the boundary conditions are satisfied by phi naught itself. The rest of the terms are 0. Now, moving on to the next slide, assuming that the things which are being done is clear to you all. Having taking another look at the boundary conditions, in this particular slide, we are basically going to repeat what we have done so far. We have the first boundary condition at x is equal to 1. The value of u is known. And the solution which we get is phi naught at 1 is equal to 2. And rest of the phi's are 0. The other boundary condition is at x is equal to 2, given by this expression. So the differential of phi naught multiplied by x evaluated at x is equal to 2 is equal to half, and rest of the differentials are 0. Therefore, the boundary conditions are satisfied by phi naught itself. Now, the conclusion which we are going to draw at this particular point is that since phi 1, phi 2, phi 3, etc. are 0 at both the points where the boundary conditions are given, the thing is unknown terms such as A1, A2, A3, and so on can have any value, and despite the fact that A1, A2, and A3 can have any value, the trial function is going to satisfy the given boundary condition. Now this is important. The thing is that since phi 1, phi 2, phi 3, so on are 0 at both the points where the boundary condition has been prescribed, we can conclude that A1, A2, A3 can have any numerical value and still the trial function is going to satisfy the two boundary conditions which are given. So this is a very important conclusion which we have drawn over here. Now moving on to the next slide. In the next slides, we will solve the differential equation taking a actual trial function. We are going to assume that the trial function has a given number of terms, and then we will actually solve the entire problem which we have taken. And at this particular point, let me remind you that in the next slide, the problem which is supposed to be solved by you all is also going to be on display, and I'm going to explain the problem also. So this is the problem. We have a domain, one line domain, one dimensional domain. The endpoints are XA and XB. The differential equation is the same differential equation which we have taken earlier. And we have the same boundary conditions which we had taken earlier. But now we are going to take some specific numbers of terms in the trial function. So let us assume that the trial function which has been taken is a cubic polynomial containing 4 terms, that is, because we have a power of x raised to 3 in this particular equation. So the trial function is a cubic polynomial. Also notice that the first term, which has only a1, is not multiplied by any x. So we have a complete cubic polynomial. And now I am explaining the particular problem which is supposed to be solved by all of you. So if the problem is not clear at this particular point, so kindly let me know. So I'm explaining the problem now. So we have a second order differential equation on display, and in the right hand side, the term which is appearing is 2 divided by x square. The term which we are getting is 2 divided by x square. Now all of you have some roll numbers. Obviously you have been assigned your roll numbers. So in place of 2 on the right hand side, that is, you are supposed to substitute the last 2 digits of your roll number and solve the entire problem with the help of the methods which are going to be explained in today's lecture. Okay. In the right hand side, in place of 2, write the last 2 digits of your roll number and solve the entire problem for the methods which are going to be explained in today's lecture. So this is your assignment, which is supposed to be completed in 2 days are going to be enough, I suppose. So somewhere about tomorrow evening, I should have all your solutions in the Google Drive. So I suppose the problem is clear. So let me proceed further. Now the trial function which you have chosen happens to be a cubic polynomial, and I'm going to illustrate now the solution procedure for the problem on display. So we have the cubic polynomial written in yellow somewhere at the top. It is written in yellow because it has been carried forward from the previous exercise. I have already told you earlier that in my style of presentation, I am going to carry forward plenty of equations which have been discussed previously in previous slides, and all those equations are going to be displayed in the top as we have over here, and they are going to be separated from the rest of the presentation by a dark line as we have in this particular case. So this is the polynomial which is supposed to satisfy the boundary condition. So we are moving now to the first boundary condition given at x is equal to 1, u1 is equal to 2, which gives equation number 1 as the constrained equation. I am substituting the value of x is equal to 1 in the trial polynomial, and I get equation number 1 as a first constrained equation. Now coming to the second boundary condition given at x is equal to 2, this is the boundary condition which has to be satisfied, and if I manipulate the trial function, I can get the second constraint equation which is now on display. Okay, I don't think this is uh, equation number 1 and equation number 2 are going to be any problem to you students, because they are simple mathematical manipulations. So we move on further. Equation number 1 and equation number 2 are the constraint equation, and note that there are only two constraints, that is equation number 1 and equation number 2, but there are four unknowns. The four unknowns are A1, A2, A3, and A4. So since we have two equations, we have four unknowns. Obviously, the four unknowns cannot be solved unless we have some other information available to us. But for the time being, we can eliminate A1 and A2 from equation number 1 and 2 and substitute them back in the cubic polynomial given by equation number 0. Okay, we can get the value of A1 and A2 from equation number 1 and 2, and we can substitute them back in equation number 0. And if we do this particular process, the trial function now is going to have a different form given by the equation on display. And if we compare the trial function with the initial trial function which we had on display, you can assume that phi naught, phi 1, and phi 2 are going to be given by these expression. Okay, what we have done is that we have two constraint equations, equation number 1 and equation number 2. These two constraints equation have been substituted. The value of A1 and A2 have been substituted from these two equations in equation number 0 to give a modified form of the trial equation. And then on comparing, we have the value of phi naught, phi 1, and phi 2, which are on display now. But the thing is, we still have two unknowns, which now are represented by A1 and A2. Because initially we started with four unknowns, A1, A2, A3, and A4. We substituted A1 and A2, and we were left with two unknowns, A3 and A4. So we can reassign these A3 and A4 to be A1 and A2. So now we have a polynomial which is in terms of A1 and A2 now. In the coming slides, we will discuss different methods available to get the values of unknown parameter in the trial functions. Now, in the coming slides, we are going to have a look at the different functions, different methods, which we are going to discuss in our course curriculum, which are going to be used to obtain the unknown parameters present in the trial functions. And these methods basically are clubbed under the under a general category of functions known as methods of weight residuals. जो method हम लोग पढ़ेंगे, all these methods collectively are clubbed together under a family of methods known as methods of weight residuals. In fact, there happen to be plenty of methods available, and out of all those methods available, we are going to study only 4 of them. But believe me, there are plenty of methods and all of them are actual working methods. ऐसा नहीं है कि the particular methods which we are going to discuss in the class, they are the only methods which are successful or which should be used. The thing is, there happen to be plenty of methods available, and you can choose any method to obtain the solution of the unknown parameters in the trial function. So we have the governing equation, and then we develop a concept of residual. Okay. For the governing equation on display, we now are going to develop a concept of residual. Now the thing is that in this particular governing equation, if you know the exact solution of u, if that particular exact solution is substituted in the governing equation, then obviously the left hand side and the right hand side are going to be same, and the residual is going to be 0. This residual is going to be 0 for every value of x in the domain. So for the exact solution u, the residual, which is basically given by the subtraction of the terms appearing in the left and on the right, this is going to be 0. And this is 0 because we know the exact solution to the problem. But the thing is, we do not know the exact solution to the problem. We basically know an approximation to the solution. So the exact solution now is represented by u, and the approximate solution is represented by u bar, which is on display. And the approximate solution itself is given by the polynomial which we have developed in the previous slides. So we have the approximate solution to the problem. And when this particular approximate solution is substituted in the governing equation, the residual is not going to be equal to 0. Okay? Since we have assumed an approximate solution to the exact solution, when we substitute the approximate solution in the governing equation, the residual is not going to be equal to 0. And any numerical method which we are going to study basically aims to reduce the residual over the domain. हम जो भी मेथड पढ़ेंगे unknown parameters को निकालने के लिए, all those methods are going to reduce the residual, is going to minimize the residual over the domain. Please note that residual is not a particular one value. Residual itself is a function of x over the domain. So you can very well plot the residual as a function of x over the domain itself. आप लोग अगर चाहें तो रेसिडुअल को डोमेन के ऊपर प्लॉट भी कर सकते हैं. Anyhow, coming to the next slide. So we have the equation of the residual. The main idea of weighted residual method is to choose the values of A1 and A2 such that the residual is as close to zero as possible, of course, for all values of x in the entire domain. The main idea of choosing the main idea of a weighted residual method is to choose the values of A1 and A2 such that the residual becomes as close as possible to zero for all values of x in the entire domain. And this particular thing, this particular aim is going to be achieved in this particular lecture by 4 methods. The first method is known as the collocation method. The second method is the subdomain method. The third happens to be the least square method. And the fourth method happens to be the Gallatin method. These are the 4 methods, that is the collocation, subdomain, least square method, and the Gallatin method, which we are going to study under the course of finite element. In fact, there is going to be a 5th method also, known as the Rayleigh-Ritz method, but that particular method does not lies under the category of weighted residual method. So that is going to be studied later on. But under this category of weighted residual methods, there are 4 methods which are going to be studied: collocation, subdomain, least square, and the Gallatin. Using all these 4 methods, we are going to obtain the value of the 2 unknowns which are given by A1 and A2. So coming to the first method, that is the collocation method. Now this, among the 4 methods, collocation method happens to be the easiest one. And the statement of this method is on display. As there are 2 unknown A's, we are going to evaluate the residual at these 2 locations. Now, we are going to evaluate the residual at 2 locations evenly spread in the domain. As there are only 2 unknowns, we are going to evaluate the residual at 2 locations, and these 2 locations themselves are going to be evenly spread over the domain. And since the domain happens to be from x is equal to 1 to x is equal to 2, the 2 points where the residual is going to be evaluated is going to be at x is equal to 4 by 3 and x is equal to 5 by 3. That means that the 2 points are at a distance of 1 by 3 in the domain itself. They are centrally placed. They are centrally placed, and the distance between the two nodes happen to be 1 by 3. So if we evaluate the residual at these 2 points, we are going to get 2 equations. Since we are trying to minimize the residual, the value of residual is supposed to be 0 at these 2 points, and this is going to give us 2 equations, 2 linear simultaneous equations containing 2 unknowns, A1 and A2, which can be solved to get the value of A1 and A2. So this is the first method for which the solution have to be obtained by all of you. The only thing is that in the governing equation on the right hand side, in place of a number 2, you are going to substitute your roll number, last 2 digits of your roll number, and you are going to obtain the value of A1 and A2 using the first method, which is the collocation method. And then you are going to plot the result, that is result of U itself and the result of flux, that is du by dx, not du by dx, x multiplied by du by dx over the entire domain starting from x is equal to 1 to x is equal to 2. So this is the first exercise. Now coming to the second method, which happens to be the subdomain method. Now in subdomain method, which is a slightly better version of the collocation method, depending upon the number of unknowns, we are choosing a small interval given by delta x and force the average of the residual in each interval to be 0. The interval delta x is called the subdomain. In this particular method, we are going to choose a particular interval represented by delta x. Delta x obviously is going to be a very small number, something of the type, let's say 1% of the length of the domain itself. So since the length of the domain happens to be 1, delta x can be 1% of the length 1. So this is how delta x can be evaluated. And then what we are supposed to do is, we are supposed to average the residual in each interval. ठीक है? Residual को integrate करेंगे. That is, once you integrate the residual, you are going to get the summation of residual, and then it is supposed to be divided by delta x also. So that is going to give you the average value of residual, and this is supposed to be equated to 0. So we are going to have 2 subdomains because we have 2 unknowns, and this is going to give us 2 linear simultaneous equation for which the solution can be achieved. The particular formula or the method is on display. We integrate the residual over delta x1 and delta x2 and divide them by the length of the domain itself and equate the result to 0. So this is the average of the residual. This is going to give us 2 linear simultaneous equations, and then they are supposed to be equated to 0 to get the value of A1 and A2. Obviously, the A1 and A2 which is on display at the moment depends upon the numerical value of delta x also and the location of delta x also. It depends upon the numerical value of delta x and also upon the location of delta x also. And in the next slide, as we have done for the collocation method, in the next slide, that is, this particular input is going to come from towards your side. From your side, we are going to plot the value of U and flux, and then we are going to compare the solution which has been achieved with the solution which was obtained from the collocation method and from the exact solution also. So this is where we stop now, and we are going to continue with the with some more portion of the lecture later, at a later time, the time for which is going to be told to you in the WhatsApp group. And before we are going to start with the remaining of the lecture, I will be asking if you have any queries to be clarified. So before we actually start with the remaining of the lecture, in some other class today, the time of which is going to be communicated to you in the WhatsApp group. If you have any queries, kindly post them in the WhatsApp group so that I can clarify them before I actually start with the remaining of my lecture. So that's all for the time being. Have a nice day.